So it's week 2, Tuesday, first lecture, and before we get into some of the textbook, we're just going to take this opportunity to do a sample problem. Tim Chester's come up with something that's pretty relevant and very much in line, I should also mention, with our summary one. It's just comparing different energy sources, and this is going to be a good warm-up for a lot of the problems that you're going to see in your problem sets this semester. So we figure we just kind of get you thinking this way. I'm going to point the camera towards Tim and mess around with the backlighting a little bit and see how it goes. So go ahead there, Tim.
Okay. And this problem is actually, this information came from, I believe it's chapter 2 in your book. It's one of the tables. I didn't write down what table it was. But it talks about world energy in 2013 and what percentage of each source of energy was used. So coal made up about 31% of all energy used. 6,675 million tons of coal was used, or about 137.3 exajoules of energy. A 5 megawatt wind turbine operates at about 25% of rated capacity. So rated capacity means it's running 24 hours a day, 365 days a year, producing maximum power that entire time. Well, they don't actually run at that. They run at about 25% of that rated capacity. So the 25% of that rated capacity works out to be about 11 million kilowatt hours per year. So how many wind turbines do we need if we want to replace coal energy completely? And we're assuming that we have all kinds of space and it's an ideal location for wind turbines and everything works like it's supposed to. We won't mess with any other variables that mess with it. So looking at that problem, what information in that problem is useful to us? Is there any extra information that we don't need?
Yeah, the 6675 million tons, because you already got the translation into 137.3 exajoules.
Okay.
So,
Yep, exactly. We could use either one of these numbers, right?
Mm-hmm.
But which one of these numbers is going to be easier to convert? Because I'm looking for kilowatt hours, right?
Exajoules.
So the exajoules is much easier to convert than metric tons or million tons. Now, if I did want to convert that, could I do, say I wanted how much oil do I want instead of wind turbines? Now this number is kind of worthless, and let's go with this one because we can do the oil equivalent. So, yeah, for this problem, we don't need that number. That's extra because it says the same thing twice.
5 miles an hour, 25% are basically useless as well, because it's just a statement. It has nothing to do with what we're trying to achieve.
Sure, the 5 megawatt wind turbine and 25% of rated capacity. Those don't really matter because the number that matters that we're going to use is 11 million kilowatt hours per year. So coal gives us 137.3 exajoules. That one's a useful number. 11 million kilowatt hours per year. That's a useful number, right? So what do we want to do with, now that we know two values, what value do I want to come up with? What's my X or Y or whatever in this problem?
Kilowatt hours. Or no, I mean total number of wind turbines.
Yep. So we have up here, this is coal, and I'm just going to label them so we know what that is. 137.3 exajoules. That's good information. 11 million kilowatt hours. Whoops. That's useful information.
Can I have you?
Yeah. So our variable in this, our unknown, is how many wind turbines. Okay? So what steps do I need to do in this? Are these numbers usable as is?
No.
No. So what numbers do I need to play? Are any of these numbers useful as is?
Yes.
Which one?
11 million kilowatt hours.
Okay, this one is good. I don't need to do any kind of conversion or anything with that number, right? I can work with that one as is. So what do I need to do with exajoules so the two of them will work together in an equation?
Convert it to kilowatt hours.
Okay? So I need to, this one needs to be converted.
That's actually where I had the issue, and what I did was obviously probably wrong, because megajoules is 10 to the 6th, exajoules is 10 to the 8th, so I literally just times it by 3 and then did my division. I'm seeing that that's probably wrong.
Oh, we're using table A2 there in the book then? Is that
Yeah.
what you're looking at?
Table
Table
A1.
A2. Oh, and A1 also to get, you had to use your X. X is 10 to the 18th too, not A.
Yeah, which is 3, I mean, yeah, but I'm pretty sure that probably doesn't work out the way 6 into 18 works out.
Right. So, I want to convert exajoules to kilowatt hours, and that's page 624, 625 in the book. Tells you how to do that. But it gives you a value for megajoules. So how do I convert? Can I convert exajoules to megajoules?
No. Well, you can, you just have to convert it to meg.
Okay, how do I convert that to megajoules? I've got
Find the difference in power.
37.3 exajoules, and I want that in megajoules. How do I get there? What's the difference between an exajoule and megajoule?
Power of 12.
Zeros, right?
12 decimal places. Or
Just-
13 decimal
Just
places.
a whole lot of zeros, right? So my exajoule has 18 zeros on it, my megajoules has 6 zeros on it. So if I add 12 zeros to my exajoules, what's that give me? Megajoules? So we're just getting them all in the same. Six, 7, 8, 9, 10, 12. Put my commas in there. And I have megajoules, right? So that's a number I can work with because I have a conversion for megajoules that shows me that 1 megajoule equals 0.2778 kilowatt hours. And, oh, look, that's the same number I've got up here. So now we're using like numbers, if I can get that to that. So, if I take this number, is now megajoules, multiply that times 0.2778
494
kilowatt
quadrillion.
hours, oops. Kilowatt hours per megajoule, per 1 megajoule. And it's critical that I put that on there because I need to get like numbers. I want my kilowatt hours. But if you look at your equation, those cancel out. And once I do this multiplication, everything's in kilowatt hours, and now I can compare them, right? So, somebody do the math on that. What did you come up with for a number for that?
494? I don't know that that's math. That's just what it came up with.
3.81, I mean, do we want to round or
Let's just keep it as is.
3.814, 194 times 10 to the 14th?
Okay. And now we already know this, right? We know 11 million per wind turbine. So,
So that's how many kilowatt hours coal produces.
correct. So I need to figure out my equation to figure out wind turbines. What's my equation gonna look like on this? Define my x, and I wanna keep my x over here, right? So x equals that number right there, 3.814194 times 10 to the 14th kilowatt hours divided by 11 million, right? Kilowatt hours, again, those are gonna cancel out. And X is the number of wind turbines, and what did we come up with for that number?
34,674,490.91, so that'd be
491.
You can't have 0.9 of a wind turbine.
Well, at the same time, we'll have some education, and somebody will turn off their lights every night, so we can get away with 1 month. Yeah, so our value there was wind turbines. So we need 34,674,491 wind turbines, and we can just stop coal tomorrow.
Is that global coal? I think that's global coal, right?
That is global
Makes
coal.
sense, yeah, okay. Mhm.
So, and then we took the problem a little bit farther for the guys that got it done quick. If you figured an average of 5 acres per wind turbine, which is what the standard is you need about 5 acres to have room for the access roads, for the, 90-foot blades if these things turn in opposite directions so they don't ever contact each other. And how many acres do we need for that?
173,372,454.5.
73 million, or it was 270,000 square miles, something like that. It's a big number. It's a big number. And as you sit here and start doing this math, I started out doing this.
270,000.
270,000 square miles. So how big is Montana in square miles?
20 million acres, I think.
Okay, so we had it in acres, so that's, we need 173 million acres.
So about 8 Montanas?
Yeah, about eight Montanas full of wind turbines every 5 acres.
Sounds about right.
Really
That
isn't
seems
that
reasonable.
Practical.
I don't know why we haven't started.
We're working on it, yeah.
And you know what, you want really scary numbers, I originally figured this up, I was gonna have you do the solar panels that were like in this week's project, or your practice problems, the 2.3 kilowatt system, and how many of those 2.3 kilowatt solar arrays would it take?
So that means there was.
And I've got it written down here somewhere, we'll cut right to the chase.
We'll just say
1.4 billion of those solar arrays, like the one on Wilmington building, to get rid of coal. Can you figure each one of those takes up, probably about half this classroom for a footprint?
Yeah, guys, tell me quickly, how many turbines per person, or how many people per turbine, if on that guy? So
How many people are there?
divide that into 7 billion. Yeah, about 200, yeah, right. So that's not too bad. You got 200 people per turbine.
About
Yeah.
$5 million.
For the entire.
Yeah.
Well, forever.
Yeah, forever.
Well,
Yeah.
And about $5 million to install it, how much is that per person? We can break down numbers all day long, about 250,000 per person, 25,000.
Perfect. I'm gonna just take a second and solve it too.
Put this back down, did you get all this down?
Yeah, let me just,
25,000 per person. And you have this. Well, minus, not including maintenance costs and things like that. but-
Yeah, exactly, and then what, 30-year life? So you're gonna have to do probably 2.5 of those for the average person's lifespan.
Is that what the lifespan of the
Yeah, so you're looking at 50,000. But you know what, I don't think 50,000 for electricity cost for your entire life is unreasonable.
Well, people are paying that to put in geothermal systems and stuff.
Right.
In their new homes.
These candles,
Yeah.
done.
There's going retro, there's a problem on candle efficiency in the book, might make you change your mind. but-
I'm just gonna live by the.
You gonna make them out of your own earwax?
This was actually quite useful. I used this in my politics and the environment class over on the main campus. You had to have a debate at the end of the semester over pro-wind turbine, or wind energy and anti-wind energy, and they decided that they'd put me on the anti-wind energy, which is good because, I mean, energy is, our knowledge is a very useful tool that you'll find that you can work it both ways, because I can find numbers on the internet to match any side of the equation that I want. And what we did was we took how much electricity does Missoula use in a year, and we took just purely residential power, nothing commercial, and figured out how many wind turbines we need on that 5 acres. We would have wind turbines from the Clark Fork River over by McClay Flats, all the way out to I-90, from Reserve Street, all the way almost to Alberton. Solid wind turbines every 5 acres. And that would only be enough electricity for the residential use in Missoula. And that's assuming we had perfect wind in Missoula and everything. So we used that as our argument to put that debate out there for the anti-wind, that we just don't have the space for it. In reality, could we do better than that? Yeah, probably, but that wasn't my argument. Oh, and it was the other interesting number I threw in just for the United States. We wanted to replace all power, we wanted to all come from wind and nothing else. It was $71 trillion for wind, with our deficit, our national deficit being 17 trillion right now. So 5 times the national deficit to switch over to wind.
That's provided that the wind patterns and everything.
And provided everything works.
There was enough places with wind patterns to put all those.
Sure. So it's actually kind of fun to throw all that stuff out there, and just be aware that those numbers can work for you in multiple ways. You can use that into your advantage. You can use it against you. You can manipulate numbers. Absolutely.
Okay, what was the number of kilowatt hours per turbine there? 11 million? Let's see if I'm going to do this right. Okay, so the way Tim worked it through it, nothing wrong with that one whatsoever. He kind of took it a chunk at a time, and I really like the way he just kind of got rid of some of the extraneous information right off the top. In fact, I think that was your question right out of the blocks there, Ray. It's like, what are we going to do with the 67 or 66, 75 million tons? But then you realize, oh, it's redundant information.
Because you can actually write them.
Yeah,
Equal
right,
sign.
the two are equal each other. So, what I'm going to show you, I think I wrote this out correctly. I kind of just did it in one fell swoop, and I think what Tim was mentioning, when you get to Brian Kern's 241, he's going to have problems that have way more steps than this. But you can tell that, well, I mean, really, you really only have one equation and one unknown. The rest of it is just is conversion. So we know that at the end of the problem, this is that third variable that you mentioned, what you're after is N. It's the number of wind turbines. A common error that I see people make is just confusing the numerator with the denominator. But I'm just going to start with this very first number and know that this 137.3 exajoules, that's the total amount of coal that we burn every year. I know from my textbook, and I'm looking at page 624, that I can convert very easily between exajoules and megajoules, and I just went ahead and put that 10 to the 12th. from here on out, the problem sort of solves itself, because I know, as I work my way through this, I'm gonna need to get rid of all the units and just come up with the number n at the end of the day. So I'm already kind of eliminating exajoules as I go.
Just multiply straight across and then divide at the end, right?
That's right, it's just one big algebra problem, and you're kind of working, well, I want to say two problems in parallel, keeping track of the numbers and the units, but it's a little more subtle than that. It's almost like three problems in parallel, because we're keeping track of the numbers, just the my dear Aunt Sally, just the arithmetic. You're keeping track of the powers of 10. And we're doing that in a couple different ways. One is, well, here's 10 to the 12th, you see that one. You can also see your megas, your x's, et cetera, just your abbreviation for power of 10, kilo, et cetera, on down the line. And then finally, you're keeping track of units. And I think until you realize that you're actually solving these three problems in parallel, it can become this kind of swirly alphabet soup. But you can see as I come through here, I am actually canceling, well, in fact, when I cancel this exajoule, I'm more or less just canceling a unit. And, obviously one example is a joule there, another one is a kilowatt hour. If we had, we did a little problem with calories last time, so you're keeping track of that. So it's really kind of three problems that you're solving in parallel. And I don't know of an easier way to do it. I'm looking at the way Tim solved it just about as simply as possible. And, he was doing the same thing. The powers of 10 going around, he had the arithmetic, and he had his units he was trying to go to. So what I'm showing here is one way to have a full accounting sheet of the whole problem right in front of you. I also do like solving it stepwise the way Tim does. There's nothing wrong with either way, and in fact, it might behoove you to just do it both ways. If you get the same answer, chances are you got it right. If you got two different answers, well, go back and check. So from there, and then also in the book, I know that there are 0.2778 kilowatt hours and 1 megajoule. So now I can cancel my megajoules. This one, so all this is just these middle two chunks are just straight up conversion, no problem. The last one, I was a little confused when I first looked at it, but if you stare at the sort of the numerator and the denominator, that top left numerator, the 137.3, and just try both scenarios in your head. Say, well, gosh, if that number got bigger, is n going to go up or is it going to go down? Well, it's in the numerator, so if the numerator on the right-hand side goes up, the number on the left-hand side has to go up. So I know I've got that thing in the right place. Now this very last denominator down here, this 11 million kilowatt hours, I'm scratching my head. Most of these numbers are not that easy to think about. You can't just visualize that many kilowatt hours. You have to trust the math. So, but think about this. If this was a 1 kilowatt turbine, little, or like say a 10 kilowatt, like a 1 kilowatt turbine like we've got back here in the bullpen, you're going to need more turbines or less? A lot more. So the fact that you got your big number in the denominator is a good thing. The bigger that number gets, the fewer turbines you're going to get. So just think it through in that scenario. Do I have the big number in the denominator properly? And just go to the extreme and say, well, gosh, what if that was a 1 kilowatt turbine? Well, shoot, you need a heck of a lot more of them. So I'm not just writing this. I mean, obviously, at this point, most people could solve this problem, but setting it up in the first place is the challenge. That's why Tim spends much time kind of going through the language. That's why I thought this thing through the way I did. So now we can confidently cancel our kilowatt hours, And then, and I saw you guys turning to your calculators, or I'm just gonna use Microsoft Excel.
And when you multiply that out, it gives you 10 to the 13, not 10 to the 14.
There's an extra zero.
I think the one we did on the board might have had an extra zero in it.
Yeah.
Because I think we were 137.3, and I think we snuck an extra. So we'll just go through it, double check both of them.
Well, it was a difference of 12, and we put 12 zeros, but not 12 decimal places, because we had to move the decimal one.
Yeah,
So it's really been 11 zeros.
Yeah, I think that's right, so let's just check it out. So I'm gonna go ahead and do equals 137.3 times 1E12, that's the way to write, what's that, a trillion, times 0.2778 divided by 11 million. And another trick in Microsoft Excel, just for formatting, I'm going to hit Control-1, and that's going to bring up the little number format. I'll click on number, I'll get rid of those 2 decimal places, I'll put in a comma, and so I got 3 million.
Yeah, so that's just spot on, it's just
off by
a factor.
Okay.
That significantly keeps the amount of winter instead of 34 million, you only need 3.
So we only need one Montana, is that what it comes down to? Can we donate Montana to global wind power?
And that's what you'll find, a lot of times your errors are going to be in this, it ends up exactly the same number, just one less zero or one more zero. So if you're looking at it, you're scratching your head going, no, that doesn't seem right. Take a look at it, because that's probably where your error is, it's probably in the zero somewhere next to it.
Yeah,
We only need 17 million acres.
I like it though, because
That's a lot
that
better
shows
than
both ways of going about it,
173
certain problems that are easier one way or the other.
Yeah.
Just have a second option to
Yeah.
solve the problem.
yeah, do it both, I mean, and seriously, do it both ways, one step at a time, little chunks. I've just become accustomed to on this type of problem, is trying to put it all on one line. You won't always be able to do that either, you might, or even break it down into digestible pieces.
And the advantage of this system over that system is if I make a mistake in my very first conversion, which we did, your entire equation is wrong now all the way through. There's less chance for error the way Brad has this laid out, because there's less, you're basically doing one calculation once you cancel everything out. There's still room for error, but not as great.
Yeah.
And if you write everything down and you do realize you made that error with just the zero, you can easily fix that in your answer.
Yeah.
The numbers
There's-
are the same.
Yeah, there's one more question, I think, David, you had this one, is how many significant digits to use? And I think in this case, really all you are allowed to use, or properly, you just use 2 significant digits, because on that wind turbine at 11 million, there are only 2 sig digs, so your answer here would be, your final answer would be 3.5 million. Right, exactly.
Not
that,
that big of a number, is close enough.
yeah, there you go. Does that make sense though in terms of significant digits? Since this guy only has 2, that's the highest number of significant digits you
It's
can
another
answer.
13,000.
It's a pretty good number, yeah, I think when I was first started looking into this, I think if you put solar panels over the entire state of Texas, that is just about enough to at least take care of the US.
Yeah, I figured 2 Nevadas, so
Yeah.
that's probably about right.
Yeah.
And my uncle ran our ranch, he runs our ranch, well, did until he passed away, completely off of hydro, solar, and wind.
Okay,
And he told me that hydro was way better than wind or solar.
better in what sense?
more efficient, he got more energy out of it by just the creek that ran through the yard than he did
Depends on
with his wind or his
process
solar.
of it.
Is that just basically dependent upon where you're at, the flow of water is against what your wind and everything is?
Yeah.
Or is it just, or is it more efficient?
Well, that's more of an NRG 102 question, but the hydropower, the generators themselves are more efficient. You know, they can run in the 85, 95% efficiency range, whereas the fundamental limit on a wind turbine is 57%, and most solar panels struggle to get up to 20%. The other nice thing about the hydro is you got a big gravity bank sitting right there, depending on, you know, if you actually have a dam, you can predict the future in terms of how much energy you're gonna have. In terms of the wind and sun, it's much more variable. So unless you have storage, and we'll get into storage in NRGY 214, you are much more susceptible to the vagaries of nature.
Compared to, you know, your solar.
Yeah, and what we'll also see later, there's one of the world's largest pump storage facilities is going in right here in Montana. It's an 800 megawatt pump storage facility, and it wasn't just like, hey, we need to build some storage. It was like, hey, we really want to build some wind turbines, but where are we going to put the energy? We can't just pipe it out all the time. So that was the answer to that. All right, well, that was a great intro to today's lecture. I'm just going to take a quick pause, and then I want to make sure we cover, I don't know, the rest of chapter 1 today. I'm going to float through the figures, and then we'll cover as much as we can. Well, we'll cover more or less all of chapter 2 on Thursday. Then I'm going to launch you off into the first exam. So Tim's actually been rewriting the exams. I think we had a lot of questions on there. Well, in some cases, too many questions. He's going to replace a couple of them with more questions like this, so that it's not just memorization. You're actually sitting down and working through some problems. So I'll take a quick break and be right back.
On the Moodle page, are they in class?